the next intermediate we're going to be learning about are free radicals. So free radicals, unlike carbanions and carbocations, which are formed by heterolytic fission, free radical is formed by homolytic fission. So homolytic fission's basic reaction is if you have, A and B bound to each other, due to the homolytic fission, they lead to the formation of a free radical. A free radical are atoms or groups of atoms which have an unpaired electron, and they are formed and they're formed by homolytic fission, and because of their extreme reactivity, or rather the tendency of an electron to pair up, these are highly reactive in nature, and they are very short-lived, and it's quite difficult for us to actually study them in detail. So let's take, for example, a chlorine free radical is formed due to the attack of light, and this leads to the formation of two free radicals of chlorine. So two, or rather let me just write it separately. So you have Cl plus Cl. Now the free radical of chlorine is going to attack methane, and what happens is this leads to the breaking of one of the bonds, and since chlorine already has one electron free, it will just take one electron with the hydrogen. So this bond is going to be it's going to undergo homolytic fission to lead to the formation of a methyl free radical plus HCl. So in first step we have chlorine molecule, and that's undergoing homolytic fission in the presence of light, leading to the formation of two chlorine free radicals. This in turn is attacking the methane, and one of the hydrogens is going to go away with one of the electrons of this bond, and leaving behind just one electron with the carbon, causing the formation of a free radical. Now, similar to carbanions and carbocations, we have classification of free radicals as primary, secondary, and tertiary. So this is going to be the methyl free radical. Only hydrogen atoms are attached to it. In case of primary, you have one CH3 group attached. This is basically an ethyl. Next you have an isopropyl. And then you have tertiary butyl free radical. So this is methyl, primary, secondary, and tertiary. Now we're not going to be talking about inductive effect, but we're going to be talking about hyperconjugation. In case of our methyl free radical, you do not have any hyperconjugative structures. In case of our primary free radical, there are 3 hydrogens, so you'll have 3 hyperconjugative structures being formed. In case of our secondary free radical, secondary or an isopropyl free radical, you have 6 hydrogen atoms, so there are 6 hyperconjugative structures. And in case of tertiary, you have 9 hydrogen atoms, so 9 hyperconjugative structures are present. And because of hyperconjugation, tertiary is more stable than secondary, which is more stable than primary, which is more stable than methyl. So the order of stability for a free radical is similar to that of the carbocation. So the order of stability due to hyperconjugation is basically the number of hyperconjugative structures which are formed. In case of our primary free radical, there are only 3. In case of secondary, there are 6. In case of tertiary, there are 9. Thereby, tertiary is more stable than secondary, which is more stable than primary, which is more stable than methyl. Now, in case of allylic and benzyl free radicals, they are stabilized by resonance. So, this is again similar to what we learned up until now. Both are allylic and benzylic free radicals. And in case of benzylic and allylic carbanions and carbocation, we studied about the fact that they are stabilized by resonance. So these free radicals are also stabilized by resonance. So CH2 double bond, CH single bond, So 1, 2, 3, 4 CH2, which is a free radical. Now what happens is this particular electron is going to shift here, right? And this bond, one of the electron is going to shift here, whereas the other electron is going to shift to this carbon. So basically you have, so here in this double bond, one of the electrons is shifting to this side. This electron and the bond's one electron is going to form a double bond, leaving a CH2 free radical on the left hand side. So this is the resonance structure. So since we have the movement of only one electron in each case, we are not using this, but we are using this. That is how we also wrote the resonance structures. Next, let's talk about the benzyl free radical. So in case of a benzyl free radical, CH2. If you would like to, you can pause the video right now and try writing the resonance structures when it's a free radical and see how you're doing. So here this will shift here, right? And this bond, one of the electron is going to shift there. Sorry. So it is going to be a half headed arrow. So, and the other one is shifting here. This leads to the movement of the free radical and a double bond on CH2. Free radical is over here. Here you have it here. So this is going to shift here. This bond is also going to shift. That's also breaking. So this will lead to the formation of a bond, right? So the bond, double bond is shifting. This and this will combine to give us this bond. You have a free radical here. You already have a bond here, CH2. Now this has to shift here. This is going to shift here and there. So you will have a free radical in the ortho position and a double bond here. Now this bond is shifting here and this electron is going to get shifted. This leads to the free radical back to the CH2 group and the electron, and we've had these resonance structures. So basically we're using half-headed arrows to show that there's only one electron which is moving. So allylic and benzylic free radicals are stabilized by resonance. Now of course you need to study about the shape of the free radicals. So here, so the shape is planar. So alkyl free radical is a planar shape and you have one of the electrons in the unhybridized orbital. So this orbital is going to be unhybridized. And this carbon is sp2 hybridized carbon. And it is forming three bonds with 3 sigma bonds with other basically hydrogen or other carbon atoms which are present. So basically a free radical is formed by homolytic fission of a covalent bond. So here in this case we studied about chlorine. So chlorine in the presence of light leads to the formation of chlorine free radical, and this on reaction with methane led to the formation of a methyl free radical. Due to the presence of due to the number of hyperconjugative structures formed in each case, tertiary is more stable than secondary, which is more stable than primary, which is more stable than methyl. Allylic and benzyl free radicals are stabilized by resonance, and the structure here you have 120. It's a planar structure. The angle between these two is 120 degrees, and it has an unhybridized orbital, and the carbon itself is sp2 hybridized. So it forms 3 bonds with 3 sigma bonds with other atoms. or it can be a carbon atom again. So with that, we complete the reaction intermediates. There are two other reaction intermediates called as carbenes, nitrines, you have benzynes. So, but then these are the basic reaction intermediates that you need to understand. In the next video, we are going to be talking about the concept of electrophile and nucleophile. Do check it out.